All right, gang, Meth 5500. All right, we're getting to the cool stuff now. Kind of built the foundation and through the end of lesson 4 and a couple of previous videos. So this is where the rubber meets the road, right? So let's pump the brakes a little bit and just establish a couple of things. All right, so we've collected some data. All right. And we know that if we have y equal to beta 0 plus beta 1x plus an error term, that we can put each of our data points into this. So we have, for the first, we have y1 is equal to beta 0 plus beta 1 x1 plus an error term. We can repeat that for the second. So beta y2 is b0 plus b1 x2 plus an error term. We can do this for all of our data points, right? We see that these y's can be expressed as a column vector. We saw previously that this part can be expressed like this. Sorry about that. And the error terms can be expressed as a column vector. So what do we have? We have a y vector, well, the y column vector times what we call our design matrix times our coefficient matrix plus our error matrix. Very, very simple algebra. We can see that the errors are equal to the y matrix minus x times the beta matrix. Okay, so we've established just a little bit of stuff that we're going to need. Now, let's go way back to lesson 1. We know, for example, that the sum of the errors is equal to 0, but the sum of the errors squared is what we minimize to get our estimates. Right? Go back to least squares. Look at MLEs. Look at, well, we also use formulas, and we've used, of course, R. And of course, this is in the simple linear regression case where we have one predictor. Now, for that reason, transitioning this into matrices, we need to examine E squared. Well, for obvious reasons, I just can't go E times E because in matrix form, my error vector is E1, E2, En, and this second would be E1, E2, En. Well, what I have here is an N by 1. An N by 1, no can do, right? So what we do is we take a look at something else, which is called the error transpose times the error. So the error transpose is just going to be E1, E2 to En times the vector, the column vector, E1, E2 down to En. So what happens here is we get E1 times, we get, again, we have, let me pump the brakes a little bit here. We have 1 times n times 1, so we can now multiply and we get a 1 by 1 result, right? Well, the 1 by 1 is just a linear combination of the rows and the columns. So E1 is E squared, E1 squared plus E2 squared plus E3 squared, and so on and so forth. So what we get is we get the sum of our errors squared from I equal 1 to n, right? So again, when we're thinking about minimizing the sum of the errors squared, our focus has to be on uh, E transpose times E. Now, let's think about that a little bit. Let's think about what E transpose E actually looks like. Well, from before, we said that E transpose, well, no, I'm sorry. We said that E was equal to y minus xb. So the column vector, the response vector, minus the product of the design matrix and the beta vectors. So we're going to have now, we're going to have y minus xb transpose times y minus xb. Now if we multiply this out, we're going to get y transpose y minus x beta transpose y minus y transpose x beta, right? Y transpose, yeah. Plus x beta transpose times x beta. Now, we're not going to mess with this first term. It's just y transpose y. But the second term, this is actually going to become beta transpose x transpose. I'll tell you what, let me just write this out. This is going to become beta transpose x transpose y. And I can take the transpose of all this, or I should say this is equivalent to beta transpose x transpose y plus beta transpose x beta. So what I get, can you guys still see? I'm getting too low. So I have y transpose y. I have such tunnel vision on this document right here that I don't look at my screen. But anyway, I have 2 beta transpose x transpose y plus beta transpose x transpose x beta. All right, so that's going to play, a critical role. Now, some of this tricky stuff I did here, let me just make sure that this is, I usually don't go this deep in a grad class, but so this y transpose x beta is the same thing as switching the reverse. So reversing the order and then take the transpose of each part of that. So again, probably something that you've seen previously. All right, let me step back just a little second. Okay, now again, recall that x transpose x is this old buddy here. And we're going to need that in moving forward. Now, I want to. I never know really how to do that. Let's call this Q. So y transpose y minus 2 beta transpose x transpose y plus beta transpose x transpose x beta. Now, what we want to do with Q is what? We want to ultimately take the partial derivatives set them equal to 0 and solve to find the maximum estimates. So what I need to be able to do is I need to ultimately take the partial of Q with respect to beta 0 and beta 1. So what I want to do is I want to dive into each part. Now, let me, again, I know where we're headed here, and I know where we're going to end up. The important thing is not what I know, it's what I can get, the information I can impart to you and share with you, get you to understand. So when I think ahead, and I'm already thinking ahead, I know I'm going to have to take the partial of Q with respect to beta. Well, beta has two parts, beta 0 and beta 1. So with respect to beta, this part right here is going to be easy to find the partial of, isn't it? Well, there's no beta 0 or beta 1. There's no beta there, so that's going to just be 0. This is going to have a beta term, and this is going to have a beta term. So my focus right now is on these two terms. What do they really look like, and what are the partials going to look like? I usually like to dive into the hardest one first. I don't know, it's just my personality. It's just the way I was made, I guess. So I want to dive into uh, this term first. So beta, that's just really ugly. I don't like that. So beta transpose X beta, what is that going to look like when we take the partial of it? Well, let's write it out. What's beta transpose going to look like? Well, that's going to be pretty easy. That's just a 1 by 2 matrix. What does X transpose look like? Well, X transpose times X, we know ad nauseum, because I've presented this I don't know how many times. And I presented it that many times because I knew this was coming. And then, so then we have a beta, which is just this term. Now, if I look at the first two matrices, here I have a 1 by 2 and I have a 2 by 2. So, the matrix, the product exists, and the resulting product is going to be a 1 by 2 matrix. Well, I'm going to take a linear combination of this. So I'm going to take row 1, column 1. So I have B0 times n plus B1 times the sum of the x's. And then I'm going to take the row 1 times column 2. So over here I'm going to have beta 0 sum of the x's plus beta 1 sum of the x squared. So this is the product here. Now I need to multiply that by beta 0, beta 1. And when I do that, I'm going to get, again, I have what? I have a 1 by 2 times a 2 by 1. So I'm just going to get a 1 by 1 matrix. So linear combination of the row and the column. So I'm going to have beta 0 times this. Looks like bond, doesn't it? Sorry. All right, simplify that a little bit. So I'm going to get a beta 0 squared times n plus beta 1 beta 0 sum x's plus beta 1 beta 0 sum x's plus so beta 1 squared sum x's squared. So this is going to leave me with beta 0 squared n plus 2 beta 1 beta 0 sum of the x's plus beta 1 sum of the x's squared, right? Let me make sure I didn't do anything silly here. Beta 1, beta, okay. All right, cool. Now, I'm going to keep that. Right here. And what I want to do now is I want to come in and take the partial of, well, this. I don't want to write all that out. So I'm just going to take the partial of this, first of all, with respect to beta 0. And then I want to take the partial of, again, this thing right there with respect to beta 1. All right, so let's do that. So if I take, with respect to beta 0, I'm going to get, again, the partial is going to be 2 times beta 0 beta n. Beta n. 2 beta 0 n. And then the next term has a beta 0 in it, so it's just going to, the derivative will just be 2 beta 1. 2 beta 1 sum of the x's. This term doesn't have a beta 0, so the partial of it will be 0. Now, with respect to beta 1, this term doesn't have a beta 1, so the partial is 0. This will be 2 beta 0 sum of the x's and plus, no, wait a minute, that's not right. So beta 1s, yeah. Okay, yeah, it is right. And then this will be just with respect to beta 1, it'd be 2 beta 1. Now, so what we have next is, I notice that this can be rewritten as 2 times the quantity well, I knew I was forgetting something kind of important, right? Kept saying that just didn't look right. So that can be rewritten this way. Now let's just justify that. I kind of forget the 2, but when we do a linear combination, we get n times b0 plus the sum of the x's times b1. Second row, we get b0 times the sum of the x's, and then we get b1 times the sum of the x's squared. And then multiply by 2, we get each one of those. So we can see an old buddy come up. This n sum x squared is just an old buddy, right? X transpose x. And of course this is just beta. So this final, this last term, let me find where I wrote it. This last term right here, let's keep in mind that the partial of this will be equal to what we just created right here. And again, the partial here with respect to beta is going to be 0. The partial of this we will create in the next video. All right, take care.